So now that I've already taken a little more time than I should have, let me just summarize what I've been talking about today. So first of all, if you don't take anything away from this talk other than the fact that black holes exist, I think that would be great. You know, they do exist, and yes, it's not just on my bank account. Okay. So, but we can also determine these masses by looking at the gravitational force from these sources. Because obviously, a black hole, if it's so compact that not even light can escape, we can't see them. But we can measure the gravitational force from them, right? We can measure how it influences the gas in the stars around them. And what we're thinking is that actually studying these supermassive black holes, it can tell us something about how these galaxies actually form and evolve early on. The one thing that we see when we look at the very most distant quasars and the distant systems is that it appears that these black holes are very, very massive, that they build up really fast in the early universe, maybe so fast that the galaxy even can't keep up. The black hole tends to grow really fast and become a very massive, very powerful quasar, yet, as I just showed you, there might be some indications that some of the galaxies can't keep up. But this is actually the subject of some future research where we're all sort of honing in on how does this black hole and the connection with the galaxy actually affect all the mass structures that we see in the universe. But a lot of this will also happen with new telescopes, like the James Webb Space Telescope. We have some new millimeter telescopes that's going to tell us more about how much molecular gas that is in the galaxies in the universe. And now Herschel is actually an infrared telescope that tells us about heat from dust and stars that are very, very low mass, and it's already flying. So thank you for your attention.
Before we take a break and listen to Kristoffer August, we have time for a few questions. So if anyone wants to ask something, please.
How many of these accretion disk spectras have you studied? Because as far as I could tell, you said there were actually heavier elements there, so that should show that the galaxy is not newborn at the time of the quasar forming.
You are very sharp. Very good. Yes. So all we know, now the spectra we can take, or it's actually from the very, very center of the galaxy. So it's actually from the accretion disk area. So all we can tell is that at least in the very center, there's been enough star formation to generate the heavy elements. However, what we're thinking, you could easily have a lot of star formation that's building up around the black hole without having the rest of the galaxy actually kind of been keeping up. So that was my point. But thank you for asking me that question such that I could make it more precise. Thank you. Yes?
What happens to all that stuff in the black hole, and can a black hole eventually die?
Yes, you can actually have a black hole starve. Imagine. But that's actually what's happening in the galaxies where you don't have any activity. So if you don't feed a black hole, it will just sit there. Unfortunately, you can't actually make it go away. There is some faint radiation that you may have heard of that's called Hawking radiation, but for the massive black holes, the time it would take to radiate away with this Hawking radiation is much, much longer than the age of the universe, so they don't really go anywhere. So they can't really die in the sense that they can't go anywhere, but they can become quiescent, they can become inactive and not actually spew out lots of particles or generate lots of energy. They can just sit there in the center of the galaxy and just make the stars move faster for the ones that are actually close to it, just like we see in our own galaxy. Yeah?
I have a question. You said in the demographics of the quasars, you find most of them, let's say, at a certain age back of the universe. Right. So, I mean, when you go to that age where they are most populous, are they, let's say, nearly every galaxy is a quasar, or are there still very few?
Very good question. Very good question. Even when we go out to the time, we call it the quasar epoch, when quasars reign and they're most numerous, there's still only a few % of the brightest galaxies.
So our galaxy was not a quasar. Or, I mean, not all galaxies have been a quasar at some point.
Probably they were, or an AGN. That's what we're thinking, that all galaxies go through a phase where matter is accreting onto the black hole. Now, we can sort of do statistics and say, okay, 1 out of a million galaxies is active. So maybe that tells us that the lifetime of a galaxy, only about 1/millionth of that was when it was active. That's how we kind of do our statistics, if all galaxies go through an active phase. And that's what we're actually thinking. Because if we have black holes, we know that you throw some matter at it, it's gonna shine. And it's gonna grow. So most likely, most galaxies had an active phase. Now our own galaxy, because it's a spiral galaxy, probably have never been, and never was, and never will be, a powerful quasar. Because we tend to see the most powerful quasars in these massive elliptical galaxies that have galaxy masses that are among the most massive in the universe. And our spiral galaxy, although it's very big, as you can see, also the black hole is not very massive. But it could still have been, you know, an AGN at some point, which we actually think it might have been. Yes?
I was wondering if a black hole can swallow, sunlight and all that kind of stuff, and it's very powerful. So how can the gas get out of it?
How can the gas get out of it? Okay, so let me let me just show that diagram again. Oops. So you're sort of thinking, how can that gas actually escape?
How can it get out? How can it escape from the
Yeah, exactly. Maybe it doesn't know that there's a black hole there. No, I'm just kidding. So one of the things that we know has to happen in order to generate a jet is that it has to be magnetic fields. Okay? So you can actually amplify a magnetic field if you squeeze all the field lines together. And most likely, gas that's coming from the outer galaxy has some magnetic fields in them, and as they get closer and closer together, they get squished closer and closer together. That could amplify the field in here. And you have something, I don't know if you've ever looked at a fan, and if you put long streamers on it and make it rotate, you see these streamers kind of do this helical motion. Yeah, so we're actually seeing the same thing in some of these sources, that the radio jet kind of has a helical type of structure. So what we're thinking actually is that these magnetic fields, if they're tied to the accretion disk here, and the accretion disk is rotating, it would actually sort of intertwine those magnetic fields and make it kind of like a tight sort of funnel kind of thing. Yeah, and plasma tends to actually travel along these magnetic field lines and get tied into it. And you can have, we actually know that in order to have matter falling onto the black hole, we need to extract a lot of energy because it comes with a lot of rotational energy when it comes from out from the galaxy. Is one of the reasons that it's actually settling into this accretion disk. Now, if you actually have winds, we actually know that that happens in some stellar systems, some compact objects, that they have winds coming off these accretion disks. That can take away some of the energy as well. Some of these winds may very well be kind of caught into this magnetic field and just be ejected again. So it's basically, black holes are very fussy eaters. Only about 10% of the material that should go onto the black hole actually makes it into the black hole. It's like little babies, very much. Not much goes down. Most of it goes all over the kitchen. And that's kind of like the black hole here. They're very fussy eaters, and you can't actually force it to overeat. It will spew out the excess, in a sense. And some of it, we believe, is how these particles are funneled into this jet. But to be quite honest, nature knows how to do this, but astronomers have not yet to date been able to actually generate a jet based on the things that we know must happen, because we know there has to be magnetic fields, because we can tell from our data that these jets are moving at relativistic speeds. We can tell that these have magnetic fields in them because of the data. So, does that answer the question? Cool. Yes?
This particle accelerator that they've now built, they're talking about generating extremely small black holes.
Mm-hmm.
Would that create a very miniature galaxy?
That'd be cool, wouldn't it? Because that would be so easy for us to study these things. No, I wish, in a sense. Or maybe I don't wish. Let me see. The bottom line, no. They can generate these miniature black holes. The thing is, with these miniature black holes, is that this particular radiation that talked about, the Hawking radiation, the timescale for the lifetime of these tiny black holes is so short, they kind of evaporate in a split second. So they're not really, we can't really generate a black hole and have it live long enough for us to study it. Sorry. Anything else?
Yeah.
Yes?
This type of science, can it be applied to a relevant, how to say, in our daily basis science? How can you use this knowledge you find and apply it to something that we can make function, either in the magnet trains or anything? Can we apply this?
I would say in maybe an indirect way, but there might be some techniques that in terms of like our analysis techniques maybe that you could apply elsewhere as well. But in the bottom line is that this type of research is what's going on to fundamental research. Actually, if we have the luxury to study how Earth came to be, how our galaxy came to be, how life came to be, we're very fortunate. So it's going on to that category of being fundamental science. So yes, directly you can't really put it into bread and butter in everyday lives. For example, if I told you that now we've found out that our galaxy is actually twice as big as we used to think it was, how's that going to change your everyday lives, right?
Yes, but maybe you could find that some things react to each other or somehow through some patterns that you could replicate or somehow.
Yes, so I think it goes more, there might be some techniques that we can apply in different ways to different parts of society in terms of industry, could be. I can't actually promise you that. We are so fortunate to be sitting in our own little bubble and looking at these very fantastic phenomena and be paid for it. Just don't tell anyone. They may take our funding away because they know we'd do it anyways. But so directly, no, I don't think that it really can be applied in such a way. But indirectly, because humans have always been curious about where we came from and how we came to be, trying to understand the nature around us, cosmos. And I think that's sort of where it comes in, that we just can't help it. Even if we can't use it for much other than settle our curiosity, we'll do it. And I'm just so fortunate that I get to do this for a living. Yeah.
I just got one comment here.
Yeah.
When Einstein sat back in the early 20th century and worked on the general theory of relativity, he had no idea that without these theories, the GPS system that we use today wouldn't work. So with fundamental science, you never know what we do. That's what we will fall out. So I think that's an important comment to make.
Yeah, that's true. That's true. Thank you for saving me there. Yes, thank you. Excellent. Anything else? I don't think Jackie wants that.
Sorry. Okay. Yeah.
It's been a real pleasure. Thank you so much.
Okay.